So here we will learn about coordinate frame mapping. So what you see here is there is point P. There is a right-handed coordinate system x, y, z. There are unit vectors in x, y, z directions which are labeled as x hat, y hat, and z hat. And the coordinates of point P are px, py, and pz. Okay. Now we will put the coordinate system to basically to uh, uh, write about a coordinate system. We will use these curly brackets. So if I have written like this 1 within these curly brackets, frame 1, so that means it refers to a coordinate system, and here that coordinate system is xyz. Okay, so this P1 written in this way, it refers to point P or description of the vector OP. So O is the origin here. Point P or description of the vector OP in frame 1. Okay, because we are not going to have one frame, we are going to have multiple frames here. So, and the description of a point in each frame is going to be different. For example, if I'm sitting in a room and I attach origin to one corner of the room, then my position will be in that frame will be different from my position in another frame which I attach to another corner in the room. Okay, so P1 refers to the position of P in coordinate frame 1. So here this vector OP or this P1 will write as 1px. So px is its x coordinate of point P, and this 1 indicates we are referring to coordinate frame 1. So 1pxx plus 1pyy plus 1pzz. Okay, that is the vector. Or if we want to write that in like a in a matrix notation, we are going to use mostly. So it will become a vector like this. The elements will be 1px, 1py, 1pz. So those are x, y, z coordinates, basically a transform of this. So it will be a column vector. Okay. So mapping is changing the description of a point or a vector from one frame to another. And we will consider three situations of mapping here. The first situation is mapping between rotated frames. So here the frame XYZ, that is labeled as frame 1, and there is another frame which is just rotated with respect to that frame UVW. They have the same origin, so it is not translated but just rotated. That is called frame UVW, and that will be referred to as frame 2. Now the description of P in frame 1, that is 1P, will be 1pxx, 1pyy, 1pzz. And description of the same point in coordinate frame 2 will be 2pu, unit vector u, 2pv, 2pz. Okay, because frame 2 unit vectors for that are uvw. Okay, and you know how to work out these things. You just take the projection of point P along x-axis, y and z, or along u, v and w. So you know that the P1 and P2, the description will be different, although it is same point. So the question here is, given this 2P or description of point P in coordinate frame 2, what will be the description of point P in coordinate frame 1? So that is the mapping we are looking at here. So if we take description of point P in frame 2 and take a dot product with unit vector in x direction, okay, that is going to give us the basically the component of this vector OP, component of this vector in x direction, and that is what 1px is. Okay, that is what the coordinate of point P. the x coordinate of that point is. So we just have to take the dot product of this OP vector with unit vector x. Okay, so here that has just been expanded, nothing fancy here. Similarly, if we take dot product of this OP vector with uh, unit vector in y direction, you will get 1p y, and similarly with unit vector in z direction, you will get 1p z. Okay, so these three equations now, they basically describe the mapping we are looking at, and those can be put in the form of a matrix. So left side you have 1px, 1py, 1pz. So that is description of point P in frame 1. And right hand side you will get this transformation matrix, which basically depends on the unit vectors for those two frames x, y, z and u, v, w. So this is a transformation matrix, and then this is this column vector. This is the description of point P in frame 2. So 2pu, 2pv, 2pw. Okay, so our mapping here is P2. Okay, this one is P2. P2 is equal to this P1, but you have to multiply this with uh, this transformation matrix 1R2. Okay, so we write this as 1R2, not as 2R1. 2R1 will be different from 1R2. Okay, and one way to actually just a way to remember that is, here we have see 1 at the top. Okay, here we have 1 and 2 at the bottom, but then another 2 at the top. So this 2 sort of cancels with 2. You can think of this in your mind in that way, just to remember whether you are going to have here 1R2 or 2R1. Okay, this 2 is at the bottom and here 2 is at the top. So this 2 cancels with this 2. Just think of it like this. It is easy to remember that. And this 1 remains. And on the left hand side, you have this 1. Okay, so 1p will be 1R2 and multiplied with this 2p, the product of these matrices, where R is called the rotational transformation matrix. And 1R2 will be written in this way. X, Y, Z are the unit vectors for frame 1. U, V, W are unit vectors for frame 2. And you see how they are, how the dot product is written. So here you have frame 1 unit vectors, you can write them in column first. X, Y, Z, X, Y, Z, X, Y, Z. Okay. And for dot product, when you take the dot product, then unit vectors for frame 2, you can write in the row UVW, UVW, UVW. Okay. So this 1 or 2 you will get in this way. Now, if you want to write 2R1, then see, then your first frame is 2, second frame is 1. So unit vectors corresponding to frame 2, you will write in column. So UVW, UVW, UVW. And for frame 1, which is the second frame here, you will write in row XYZ, XYZ, XYZ. That will be 2R1. Okay, so 1R2 is different from 2R1. That ordering is important. And you can see this, just like we wrote here, P1 is 1R2 2P. You can write this P2 equals P1, and then you will multiply this with 2R1, and you can think just like I described previously, this 1 cancels with 1, so 2 remains. Okay, this, and if you compare these expressions, you will come to some conclusions here. Okay, I'm leaving that to you. One is, you will clearly see that 2R1 is a transpose of 1R2. Okay, you'll see that just by comparing them. And other thing you will see is this RR transpose is equal to identity matrix. Okay, and you will also see this. Okay, this actually this previous one is comes directly from this, that yeah. So you can see them just by those equations clearly. So that was mapping for rotated frames. Now second is mapping between translated frames. So here you see a frame XYZ, its origin is O1, this is frame number 1. And another frame UVW, its origin is O2, this is frame number 2. So they are not rotated frames, just the origin is translated from O1 to O2. And now we want a description of point P. Okay, description of P in one frame is given. What will be the description of P in other frame? Okay, that is the problem. So here we can write vector O1P. Just look at this triangle here and you can see the vector O1P is equal to O2P plus O1O2, or alternatively you can write this as description of P in frame 1, that is P1. This is vector O1P is equal to 2P plus 1D2. This 1D2 is, you can think of as like a displacement vector 1D2 from 1 to 2, from origin of 1 to origin of 2. So from origin of 1 to origin of 2, that is vector O1 O2, that will be indicated as 1D2. Okay, and this actually mapping is very simple. You write 1P as 1P x x, 1P y y, 1P z z. Okay, and you can also write that as, just based on these vectors here, you can also write this 2pu. Okay, because u is actually oriented along x direction only, 2pu plus dx, where dx is x component of 1d2. Okay, dy is y component of 1d2, dz is z component of 1d2. Okay, it is very straightforward. So P1 will be equal to this, that is the equation, and you can write that as, just like we wrote for the rotated frames, as in a matrix form, we can write as 1P equals 1T2 2P, where this 1T2 is the transformation matrix. Okay, for the mapping here, this is the transformation matrix. Just like we had 1R2 previously, here we have 1T2. And now instead of 3 by 3 matrix, actually it is convenient to, when we want to write it in a matrix form, it is convenient to write it as this 1T2 as a 4 by 4 matrix. So left hand side you have 1px, 1py, 1pz, and just this one added. It has additional use, sometimes we'll not get into that. Then this transformation matrix is just this. So you can see first there is an identity matrix here, 3 by 3 identity matrix, and then last column is dx, dy, dz 1. Okay, which are actually components of the vector 1d2 in x, y, and z direction. And then this is 2pu, 2py, 2pw. 2 is a superscript here, it is not multiplication. Okay, that is description of point P in reference frame 2, and then 1 here. Okay, so based on this you will see that 1px will be equal to 2pu plus dx, 1py will be 2pv plus dy. That is what you will get, and that is what we have from the above equation, but here we have written that in a matrix form. And this matrix here, this 1T2 written in this way, that is called basic homogeneous translation matrix. Okay, so that is the mapping we obtain for translated frame. Okay, now look at the last one, which is mapping between rotated and translated frames. So here we have a frame XYZ, frame number 1, its origin is at O1, and we have another frame UVW, its origin is at O2. This is called frame number 2, and you can see the origin has been translated, so it is a translated frame, and UVW are not along X, Y, and Z, it is also a rotated frame. Okay, so how to get that mapping? To do that, we can consider an intermediate frame 1 dash, okay, which is x dash, y dash, z dash, this intermediate coordinate frame, and this one is just translated with respect to x, y, z, it is not rotated. Okay, and we can use the previous results we had for rotated and translated frame, because from 1 to 1 dash it is just translation, and from 1 dash to 2 it is just rotation. So we can just combine those two things and we'll get the mapping for this case. So here you can see this P1 dash, description of P in 1 dash will be description of P in 2, but multiply that with this matrix, this rotational transformation matrix, 1 dash R2. Okay, 2 will cancel with 2, so you get 1 dash R2. Okay, because 1 dash and 2 are just rotated with respect to one another, so that is just straightforward. And 1 dash R2 is same as 1 R2 because 1 and 1 dash are aligned. Okay, you already see that in the figure, they are aligned x y z, and x dash y dash z dash, they are along same direction, so 1 dash R2 will be same as 1 R2. And we can also write 1 dash P equals 1 R2 P2. Actually this, okay, we can write that because 1 dash R2 is same as 1 R2. Okay, so we write it in this way. And then we are now, so that was for the rotation part. Now we can look at the translation part. We can say vector O1P equals O2P plus O1O2, and that becomes P1 equals P1 dash plus O1O2, because from 1 to 1 dash it is just translation, and we can write that as 1P equals 1 dash P plus 1D2. Okay, 1D2 is the vector from O1 to O2. Okay, so then we can write 1P equals this 1 dash P, we can write from the previous equation, that will be 1R2 2P plus 1D2, and this whole thing, okay, this equation, we already have an expression for 1R2, we have an expression for 1D2, it has components dx, dy and dz. This whole thing can be written in a matrix form as P1 equals P2 multiplied by 1 transformation matrix 1T2, which takes care of both translation and rotation. And this 1T2 is a 4 by 4 matrix. Its first part here, this first 3 by 3, this part is actually same as 1R2. So this part corresponds to rotation. It is same as 1R2. And if you look at its last column, this corresponds to translation. It has dx, dy, dz and 1. So very easy to remember. It is a 4 by 4 matrix which is for rotated and translated frame, takes care of the mapping. One its first part here is 1R2, this is 3 by 3. Then you have 1D2 here in a column form, and then last row is just 0 0 0 1. Okay, so this for rotated and translated frame. Now sometimes we look at principal axis rotation. So what that means is our actually transformation is just, let us say, rotation about z axis by an angle theta. So in short form we just write that as RZ theta, rotation about z axis by an angle theta, and that based on this one, okay, based on this rotation transformation, that becomes this cos theta c theta, that is a short way to write cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. Okay, similarly if you have for rotation by an angle theta about x axis, then that transformation matrix becomes this, rotation about y axis, that becomes this. Actually this is based on this only, this dot product of unit vector that you saw previously, you get these. And there is an easy way to remember this. Let me tell you that. So first you can write, see, if it is rotation about z axis, then the z component of the point is not going to change, only x and y components are going to change, z will not change. So because z will not change, that is why this third row and third column corresponding to that, okay, you will have just 1 here and 0 0 0 0. Okay, and if it is rotation about x axis, then x component is not going to change, so you'll have 1 0 0 0 0. Okay, for y you'll have 0 1 0 0 1 0. Okay, so like that, that particular row and column you just write like this. And then the diagonal elements, the remaining diagonal elements will be just cos theta, cos theta. Here also you see cos theta, cos theta. Here also cos theta, cos theta. Okay. And off diagonal elements, remaining off diagonal elements will be sine theta and minus sine theta. Okay, that is what you see in all three cases: sine theta minus sine theta, sine theta minus sine theta. Okay. But now the point is, which one is going to be minus sine theta, which one is going to be sine theta? If you can remember, I have written a note here. You have to write sine theta in a row, in the row which is above the row having 1. Okay, and you have to write minus sine theta in the row which is below the row having 1. Okay, so you see here, so there was 1 here. In the row below this, you'll write minus sine theta, then what remains will be sine theta. Okay, so you have 1 here. In the row below you will write minus sine theta, and then in the row above you will write sine theta. And similarly here you have 1 here. In the row above you will write sine theta, and then what remains will be minus sine theta. So generally people just remember these principal axis rotation. We use them very frequently. Okay. Okay, now let us also talk about a little bit about the attaching the frame on the end effector. So here you can see this is an end effector, and an XYZ, or you can name them anything, XYZ, UVW, whatever. That frame is attached to end effector, and that frame is called actually NOA. Okay, so N corresponds to X, O to Y, A to Z. So that is called, instead of XYZ, it XYZ only, but it is called NOA. And what are these three N, O, and A directions? You can see those in this figure. Direction A is the approach direction. So this is the direction in which the end effector will move towards the target. So that is approach direction. Direction A. A stands for approach. Okay, direction O, that is perpendicular to this, that is called the orientation direction, orientation or sliding. Okay, so this is the direction in which these two, you can call them jaws if you want, of the of the end effector, they slide for gripping. Okay, so this is called the orientation direction. So NO, sorry, that is, we talked about A and O, and N is going to be perpendicular to both of these based on right hand rule. Okay, so you know the right hand rule, N cannot be just up or down. Okay, based on right hand rule, if your coordinate system is NOA and O and A are oriented like this, N has to be upward. Okay, and that is called the normal vector. So the frame on end effector are called NOA. Just XYZ only, but that is the convention. Okay, and if we have, so here we have a frame XYZ. Okay, and we have a frame NOA attached to the end effector. If we are looking for a transformation from XYZ to NOA, okay, this transformational matrix. So this matrix is basically going to be this only, this 1T2. But now we have this from XYZ, 1 is XYZ, 2 is NOA, and we are going to write that based on these dot products. So very simple, and it turns out to be this NX, where NX is the component of this vector N in X direction. Ny, Nz, Ox, Oy, Oz. These are components of vector O. Unit vector in direction O. If we take its component in X direction, that will be Ox, Oy, Oz, Ax, Ay, Az, Dx, Dy, Dz, 0, 0, 0, 1. So it's very easy to remember as NOAD. N is a column, Nx, Ny, Nz. Similarly, O, A, and D are columns, and 0, 0, 0, 1. Okay, so we talked about mapping here.